Day 3. So we're going to talk about the detection process today and distance sampling. But is there any question regarding why we are doing this, or what we did last week about behavior and the removal models? Was that all clear conceptually and in practice what we are doing there when we are using the breakdown of counts into multiple intervals and we are relating that to some kind of probabilistic model, right? So what we are going to do today, and just jump in if you have any questions that you feel like I should answer right now before we move on. But today's process is going to be very similar. In fact, when I wrote the function to estimate this, it's the same function. As we saw, there is a removal model and the distance sampling because it's only a slight change if you go from one to the other. So that is going to be helpful in understanding what is going on. But because time is going, well, from past to future or left to right or button to up, depending on which culture you are coming from, but it's still a one-dimensional thing. Time goes by and then something is changing along that axis. Space, we have 3 dimensions, but let's just focus on our landscape. X and Y, we have locations inside that. So once we start talking about something spatial, we need to deal with more dimensions, which just makes it a bit harder to grasp. But that's what I'm going to do in the slides to kind of get these concepts across, and then the rest is going to be easy. So, and then apart from the statistics, we are also going to talk about what is really happening and how we need to deal with that process and what we mean by the detection process. So in the meantime, just go to the website, grab the latest version of things. So if I go to code, tags, there is day 3 now. So this release, you can download the zip file, and that is going to have all that are marked down that I put together for today. So please go ahead, do that. And then of course, you can get your little local file as before. If that's something you'd like to do, just source the functions.r and type QPAD local day 3. That is going to set everything up for you for the rest of the day. So this is where we were at. We were trying to estimate these nuisance variables so that we can adjust our observed counts for these things. And as a result, then we're hoping to get abundance or density, abundance per unit area, once we take these into account. So we talked about how to estimate P, which is a quantity that relates to the time we spent collecting the information in the field. And we were using removal modeling, which is closely related to survival analysis. And now we are going to talk about this other quantity, Q, which is not quite correct. You'll see what I mean by that. Q is one way of expressing this part of the equation. But for now, this is related to the area we are sampling and not the time component. And this is going to capture how observers are going to detect things if they are available. So birds, critters need to be present, needs to be available for sampling. And then once all of these conditions is satisfied, then we have a chance of detecting them depending on our abilities, the distance between us and the individual, and so on. So the first thing, if we want to describe how this distance relationship is really working, then in a pig-centric word, there is king pig, and then distance to rat, distance to chuck. Chuck is a bit closer to king pig. And as a result, if you assume some form of distance function, which describes how the probability of detection is decreasing with distance, then we are going to see detecting Chuck is higher than the probability of detecting red, because red is farther away. So we can say King Pig is going to be less likely to detect red than Chuck. And I just want to flip this thinking around, because really what's happening is we are not hearing into the forest, but sound is coming out and we might or might not hear it, right? So the probability of detection is decreasing with increasing distance from the source of the signal, because if we shout or not shout, that sound pressure is going to eventually evaporate. And that's the function of the distance from the source of the sound, and not really distance from the observer. Although, as you can see here, the probabilities are still the same, no matter that we flip this image. Those probabilities are going to be the same, kind of capturing how likely it is going to be for King Pig to detect the two birds. But just this is an important notion, and it is going to come back later when we talk about some of the complexities involved in sound transmission. So I just wanted to put this out, and this is also a nice way of using some familiar faces to describe this relationship. Hopefully this is going to stick. Bird-centric word, and we are measuring distance from the angry birds and not distance from the pig. So then this whole detection process is often triggered by these cues, visual or auditory cues. So it depends on these individuals being available for detection. And I'm referring to the detection process as this physical aspect of a signal being emitted, and then an observer or a detector is then going to register that signal, and how strong that signal is going to be, and whether it is going to exceed the threshold that we can say, oh, I heard that. That's the physical side of things. So it comes down to physics and how sound travels through different media. So I'm not referring to the psychological process of, can I still remember writing down the third species, or can I put them in the right bin because maybe I'm estimating distance slightly off. So this measurement error or misclassification with respect to distances or species, that is part of the transcription. If you recall what kind of layers we had in the simulation landscape, that is how I think about it. There is the physical part, which is just sound travels and what happens, and then the other regards of whether we take notice of this information or how do we put that into a little table.
Peter?
Yes, go ahead.
I don't want to jump ahead, but when you're doing multi-species surveys, I mean, it could happen that even if you account for time or P or Q area, two different species might still have different detectabilities given species traits, right? So the probability of detecting red, even if it's smaller than Chuck, be higher because of the contrast with the background environment.
Yes, so here we assume that the detection function is the same for Chuck and red, because the sound engineers made sure in the studio that this is the case. But you could quite easily imagine that maybe for Chuck, it is going to go down faster. So eventually they might still get the same detection probability, but the distances might not be the same. That's totally correct. If you're looking at individuals or different species, then this relationship might change. So the shape of the function can also vary as a result of all kinds of factors.
Yeah, and I guess it depends if you're using recordings or visual cues also. If you're using recordings, perhaps species traits are not that important, but if you have an observer, species size or background or coloration with respect to sound could kick in.
Yes.
Yeah.
Thank you. So the first and most important piece that we need if we want to model this relationship is the distance function. And let's call this g of d. D is the distance between the source of the signal and the receptor, like our ears. So g of d describes the probability of detecting an individual given the distance and then given that there is a signal to be detected. And it's a monotonic decreasing function of distance. And we also say that zero distance, the probability is 1. So there is a perfect detection. Of course, this might not be perfectly true, and we will come back to this later when we put things together. So why this couldn't be the case? When at zero distance we miss something, that might be because it's perfectly camouflaged or it is silent. And so that is that availability bias. That's why we need to combine this quantity together with P that we estimated before. That is going to influence how likely it is that we are going to detect something at zero distance. But right now, we just assume that they are available. And in that case, this is an important assumption to make. So the simplest model that one can think of is a negative exponential, which is a one parameter function. So we have g of d as e to the power minus distance over this tau, which relates to how quickly this function goes close to 0. So the probability quickly decreases at the small distance side of things. And this captures the physical process of sound attenuation under physical spreading. So if you have like a recording, then this might be a good model to fit. But oftentimes, if you're looking at humans and how they detect things, and there might be slightly higher chances of detecting things closer to us, so it's not like a totally flat shape, then we might look at this half normal, which has also some other really neat characteristics why I really like using this. It is still a one parameter function. The difference between the two is that minus d over t, here we have minus d over tau squared. So this is the difference. This is kind of changing the shape of it. So if you imagine a normal distribution, if you cut that half at the mean and kind of fold it together, that's how you get this half normal distribution. So this tau squared in the denominator is the variance of the unfolded normal distribution, and half of that is the variance of the half normal distribution. So it has slightly more shoulder, and I'm going to show it to you after we discuss the next one. So the negative exponential and the half normal is related to through this b parameter. You can also pick something that is not just 1 or 2, but it can be anything greater than 0, and that is going to kind of influence the shape of this curve. So you can also look at it as a 2 parameter family of distance functions. The third one that is also often used in the literature is the hazard rate function, which is a 2 parameter model. It's 1 minus e to the power minus distance over tau to the power minus b. And this b is affecting a more pronounced shoulder. And so this is the shoulder I'm thinking about. So you can see negative exponential goes down. Then you have the half normal, which has this slight shoulder, and then it goes down. And then the hazard rate has this really, really pronounced shoulder, which just means to a certain distance, detection is almost perfect. And then after that, it kind of like an exponential. So it goes down at much faster rate. So we have these distance functions, and later we can look at how misspecification of this distance function might affect our estimates or how much difference it makes. But for most of the cases, I'm going to use the half normal, because just parameterizing that and doing calculations is much easier with that kind of function. And we are going to see why I really love this distance function. It's just mathematically so easy, some of the equalities that you get. So now let's talk about distance sampling. So when we look at the distribution of the observed distances, then we need to take into account this detectability, which was captured by the distance function, and also the distribution of these individuals. So their location or distance relative to the observer. And so there are certain individuals or just places in space that are available for us to observe. And there's going to be that portion that we actually capture as part of, yes, detections are coming from that distance. So we need to take these two things together when we want to talk about distance sampling and turn this into a parametric model. And also this is slightly more complex for point counts, because if you're going along a line and measure distance from a line, then availability, and by availability I mean the amount of points at different distances is going to be just constant, right? If you go 1 meter or 2 meters, that's still the same line parallel to your transect. Whereas if you're at a point, then you're looking at circles, and as you move away from the point, the size of the circles is going to increase. So this is why when we work with integrals, that is going to be slightly different than from a line transect. So the area increases linearly with the radial distance. So we have this triangular distribution, and let's call this h of d. So distance, again, is d, and this function is h. And so we have the perimeter of the circle, which is distance times 2 times pi over the area. So this is how we would capture this function with distance. So then if you simplify and we also throw in something which I call R max, so the area can then be expressed by pi times R max squared. And this R max is our truncation distance. So right now, let's just think about that we are doing distance sampling over a confined area. And this area is a circle at this truncation distance. So you're just kind of putting a gigantic cookie cutter into the field, put it down, and inside the cookie cutter, like 100 meters, 200 meters, that's our world that we are going to explore. So this is what our max is referring to. So in distance sampling, we are looking at the product of the distance function, g of d, times h of d, which is how common those distances are. So if you think of it, you have just with perfect detection, independent of distance, every point is equally likely to be detected. This is when you get the same number for g of d as h of d, but g of d is going to decrease with distance, and h of d is going to increase because you just have larger and larger circles. So you get this product. This is not scaled by their area, but kind of just straight multiplied together. If you have this half normal detection function, and this is the linear function of for area h of d, and if we multiply them together, then we see it goes from 0 up, 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 then down, because at the point there is nothing really to talk about, and that's why we need to make that assumption that g of d is 1, because that function doesn't even have a value at that distance, so we just need to force it to 1. But there is no area involved, so really we are multiplying it with an infinitely small 0 value. That's why this becomes 0. then it increases because G is still high, and we are getting more and more of those areas. Then area keeps increasing, but then our detection part is going to be so low that, again, if you multiply any high number with a really, really small number, you're going to get something close to 0. So this blue line is really what we're trying to capture. That is going to give us the probability distribution that we can use to estimate the distance sampling parameters. The other important concept we need to talk about, so this was just in one dimension. So for example, if you have 10 people lined up 100 meters apart, and one is listening and all the others are yelling, then you kind of capture that along this line how things are changing, or now we kind of took that distance function, and because we incorporated that age, which is going to be like the area around the observer, then we took this distance function and kind of rotated it around. And now we are not just looking at this one-dimensional relationship with distance, but a two-dimensional relationship with distance. So you can think of it as a pie dough that is shaped like a two-dimensional normal distribution. So now let's explain what we mean by average detection. So we take this product, which is G of R and H of R, and integrate it over distance up to R max. So we increase the radius up to R max, which is the size of the cookie cutter. So now we have the pie dough, which describes this two-dimensional volume. And then a cookie cutter cuts through the dough. And now you can imagine like this. So this is the dough, and we just cut it here with a big cylinder. So this is what our integral is capturing, and we call that Q of R max, or whatever radius we are talking about. But with R max, this is just our truncation distance, and average detection is this volume inside the cookie cutter. And so the cookie cutter and its volume describes perfect detectability within that radius. And the dough inside the cookie cutter describes what we actually have as our distance function is going down. And the ratio of the two, so the dough versus the volume of the cylinder, is going to give us this average detection. So this is how much we need to account for within that area to get it back to the perfect detection level. So whatever area is missing there, that is going to be proportional to the individuals that we won't be able to detect within this distance. And that's why we call it average detection, because if we can somehow calculate this, then we have a nice way of adjusting back to the original density. So here we talk about this R max and pi times R squared, or R max squared. So this is the volume of the cookie cutter. And I really like this analogy, and you will see why. So this is how Q R max is changing with increasing R max. This is a pretty uninteresting line, but this is how we are going to then be able to calculate this adjustment factor, which is Q. So now we know really what that Q means in QPAD. We just don't know how really we are going to calculate this or estimate parameters related to this Q. That's what we are going to talk about next. So let's take again the half normal distribution. And again, don't pay huge attention to the formulas, but just now we want to describe the volume inside of that dough. And so if we have the half normal, then things simplify considerably. So again, This is what we talked about for average detectability. So we have this volume that we are interested in calculating, and then we have this whole volume. And if we know the two, then we can calculate the ratio, which is going to give us Q of R max, which is average detection. And this relates to the cell probabilities that we are going to use in the same multinomial model as we did before. So we are going to see that probably it's best to leave this for the coding part. So as we have increasing distances and these distance bins, then we are just going to get those cell probabilities, and we'll be able to then look at counts that were coming from 0 to 50 meter, 50 to 100 meter bins, and relate those back to these probabilities of related to average detection. Because you just think about it, this goes on. So if I now put an even larger cylinder around it, I get a different probability. And I can keep doing this, or I can put an even smaller one. And then that cumulative distribution that I get after increasing the size of the cookie cutter, that's how we are going to get different Q of R values, which are then going to be proportional to the counts we are getting from each of these distance bins. So now the next thing we're talking about is we have this volume of the pie, which is this tau squared times pi. And now we put a cookie cutter around it. This is a pretty uninteresting quantity because one is fixed. That just depends on the shape of this distance function. And then we have control over the cookie cutter because it's as big as our protocol says, right? But this is another metric that we can calculate. So black divided by black plus red, which is the whole area. So why this is important is because this leads us to something called EDR. EDR stands for effective detection radius. And in this case of the half normal, tau equals EDR. So if we can estimate the shape parameter tau from our distance function, then we know what our effective detection radius is. Then that gives us a way to calculate the effective detection area. So in case when the sampling area is unknown because we are using an unlimited distance count, we can still talk about this effective area sampled if we know EDR. So now to be able to show that yes, this EDR really exists and how do we get that conceptually, is we need to equate these two things that we talked about, Q and pi. And now here pi is not 3.14 something, but this is a function of radius, as in here. So we have this shape and this shape. EDR is the distance. So this is not R max that we know. This is whatever radius that EDR happens to be. EDR is the distance where the number of individuals counted outside of it equals the number of individuals missed inside of it. So where the blue, which is cylinder minus black, equals the red part. Because if you now take this cookie cutter and you have the dough inside and outside, this volume outside is going to be the same as the missing volume inside. So now you can take this dough, put it inside, and you're going to have a perfect cylinder, right? So if you count up to this distance, you can assume perfect detection. And then it drops to 0 because now we just moved all the dough inside. So this is how you can think about EDR. It is not just this distance function going in 1D and when P equals 0.5, that's our EDR. No, that's not quite correct. You need to rotate it around to get this three-dimensional shape, and imagine that you have a gigantic cookie cutter, and this is how we find EDR. We keep increasing it until we find that the two volumes, inside and outside, equal. So I think we are done with the hardest concept over the 4 days. And hopefully this helps really to get this EDR concept across. Once we have this pi function, we can also look at it as a cumulative distribution. And if we do that, this is exactly what we are going to use in distance sampling, because we have counts binned into these distances. And now, as you see these jumps, those jumps are going to be proportional to this added probability that we go as we move along the distance bins. So we can expect that the proportion of counts divided by the total is going to be proportional to these jumps. So as we move farther away, you see relatively few individuals, then more individuals, then less and less and less and less. So this is what we are going to use to calculate the cell probabilities, which we can use in a multinomial model to estimate the shape of this curve. And the simpler the shape is, the easier it is going to be to estimate it. And before I finish with the slides for today, I just wanted to show this image from our ecography paper, where we looked at constant p-values which are coming from the removal model, so really singing rates, not just the p-values. And then on the right, you see this tau from the half normal distribution, which we know now is equals to EDR. And then we looked at what we estimated from the data, and then also we used a model based on phylogenetic relatedness of the species and also some trait variables. And then we tried to predict these as a function of species traits and their how they are related to each other. And then we did some leave one out cross-validation. And you can see for singing rate, there's a tendency to be able to detect it quite okay if you know something about whether they are migrants or not. But there is a lot of variation. So it's harder to predict this based on species traits, but usually these values are within a well-defined range and lead to high probabilities over like 3, 5, 10 minutes. So this is less of an issue. However, EDR, those probabilities related to the component Q, those vary much larger across species and habitats, and that has a really huge impact on our abundance and density estimates. But luckily, you can see it's much better captured by traits and also whether they are open habitat species or forest species. And the best predictor for this detection distance relationship was body size, which again relates to how, so there's sound pressure, how, what's the word? How loud they vocalize, right? So that's why you can see crows and ravens up here. All right, so if you have a species where you don't really have the data to build a really great model, then based on traits, you can pull together data to get an average estimate for similar species, or you can use other species estimates to kind of come up with a really good proxy, at least for EDR, I would say. That should definitely work. And for the other quantity, it matters less.